This video is on a zeroth order integrated rate law. Like all rate laws, we need to take experimental data. And the experimental data here is to record the time as your x value and your concentration as your y value. What you should notice right away is something that you should be looking for, even if the numbers are a little more complex, and that is when the time changes by a certain interval, the concentration changes by a certain interval. As long as you keep that interval constant, the delta y will be constant. I made the numbers really easy so it's obvious to see. The AP will not, but you can use a calculator or do some basic subtraction to figure it out. You can pick whatever time interval you want as long as you're consistent. In this case, every second, the concentration A changes by exactly the same amount, 2. Another second passes 2. Another second passes 2, over and over again. And that's how you recognize something that's zeroth order. When you graph it, you get a straight line with a negative slope. Remember, the y-axis here is concentration, and down here you've got the time. Watch your time units. Sometimes it's seconds, sometimes it's minutes. I even see in hours, okay? Make sure they're matching, or you'll get things wrong even though you knew exactly what you were doing. Now, what this means is essentially the concentration has no effect on the rate. And that's why it's zeroth order. See the zero up here again, right? What that means is rate is basically equal to k. Now, the slope is a negative value, so we're going to have to negate that. So the slope that you would get here would be negative 2 molar s to the minus 1, right? But the rate constant would be 2 molar per second to negative 1. All right? And, that's delta y over delta x. And that basically is the rate, right? So K is the rate. It's the change in concentration over time, which is what the rate is, and it's got to be a positive value, right? So we can use that in our little equation down here. And notice, it's a straight line equation. This is y, this is m, x, and this is b, your y-intercept, right here on the graph, right? Whatever that concentration was. Once I know what the rate constant is for this reaction at a set time, temperature I mean, right? Because temperature affects the rate of a reaction, right? So as long as we don't change the temperature, I can start at any concentration and use the rate constant that I've determined experimentally to figure out other things. So for instance, if I start off with a 14 molar solution and 3 seconds pass, what would be the concentration after 3 seconds? We know it's going to go down, right? So we just plug the numbers in. And yes, the math here is really easy because I'm just trying to show you the concept. You're just plugging numbers into this equation though, right? So you have negative, the rate constant, which is 2 molar s to the minus 1 times 3 seconds. So the seconds will cancel out. You'll get molarity, right? Plus 14 molar. Okay, and this comes out to 6. So you have basically negative 6 plus 14 is what it comes out to, which is equal to 8. So the concentration at time t will be 8 molar. Obviously, if you get past 7 seconds, okay, because 7 times 2 is 14, that's where you'll cross the line where, AT is 0. A couple of things to note here where we're going to be going with this. You should be aware that when something is a zeroth order reactant, that generally means it's not in the rate determining step. It's going to be occurring during a fast step in the reaction. We're going to talk about mechanisms soon, okay, in other videos. And often chemical reactions happen in more than one step. And often things that are reactants that are zeroth order are not participants in the rate determining step. And we're going to talk about that later, but the rate determining step is a slow step, right? It's the one step that slows the process down, and it really determines how long the process takes. We'll come back to that later. That's zeroth order. It's not hard.